Okay, good afternoon, all of you. So, a very quick reminder of what we are planning to do today. Actually, today we are planning to do first law of thermodynamics, number one. Number two, we will be doing a topic called specific heats, which we were supposed to do with kinetic theory last day. We didn't do it, so that we'll do today. And finally, related to specific heats, there is a topic that is law of equipartition of energy. So these are the three things we are going to do today. So we will first do first law of thermodynamics. After that, we will do specific heats, and then later on we will do law of equipartition of energy. So these are the topics that we are going to do today. So first thing is that there is a piston. Okay, there is a piston, this is a piston, and over here there is a gas. So there is a piston and there is a gas and there is heat over here. So there is a piston and below the piston there is a gas, and here some heat is being provided. Now this heat will cause two types of changes. One is that due to this heat, the energy of the gas which is in this space will increase, right? So the energy is given by this symbol U. So U is internal energy. So U is internal energy, and internal energy is the total energy of the molecules, right? So you are supplying some heat to the gas, that is Q. U is the total energy of the gas, that is internal energy, and W is the work done by this gas. It can be something, so we can say generally we can call it a system. So you are supplying heat to the system. So due to the heat supplied, the internal energy of the system will change, and the system will be able to do some work. So like this piston is there, so the gas which is over here, it will be able to push the piston. So the heat supplied is delta Q. Actually, Q is the symbol for heat supplied. Q is the symbol for heat supplied, U is internal energy, and W is the symbol for work done. So delta Q is delta U plus delta W. So Q is the heat supplied, U is the internal energy, and W is the work done by, like W is the work done by the gas, or you can say the system. Okay, W is the work done. W is the work done by this gas, or instead of gas you can say the system. So delta Q is delta U plus delta W. Now delta W is the work done. So this gas or this system is doing some work, it is pushing the piston out. So when it is pushing the piston out, the piston is moving by an amount x. Okay, so this gas or this system is pushing the piston, so piston is moving by an amount x, and the cross section area of the piston is A. So okay, let me write delta x. So let me write delta x. So A is the cross section area of the piston, and delta x is the amount that it is moving. So A into delta x is the change in volume, and the point is that the pressure of this gas is P, pressure into area is force. So the area of the piston is A, so pressure into area is force, force into displacement is work done. So delta W is P into A into delta x, and A into delta x is the change in volume, delta V. So according to the first law of thermodynamics, the total energy of the system will be conserved. That means the total energy during the transaction will be conserved. That means if you are supplying some heat, delta Q, then partly it will be used to increase the internal energy, that is delta U. The rest will be used by this gas to do work on the piston, that is delta W. So delta Q is delta U plus delta W. And once again I am saying that when the piston moves out by delta x, so the pressure of this gas is P, pressure into area is force, force into delta x is the work done. So the work done by this gas is pressure into area into delta x, which can also be written as pressure into delta V. So delta W is equal to P into delta V. So this delta W is equal to P into delta V is the general formula for work done. Okay. Now, suppose we want to do this completely, this work done, delta W, P, delta V, we want to solve this completely. So, delta W is P into delta V. So, suppose we want to solve this completely. So, in that case, first is that if it is isobaric, isobaric means pressure is constant. Okay, so if it is isobaric, then delta W is P into delta V. So the pressure is constant. So if it is isobaric, then delta W will be equal to P into delta V. So pressure is constant. Then number 2 is isochoric. So isochoric means volume is constant. So isochoric, it means volume is constant. So delta W will be P into 0, that is 0. So isochoric means that there is no change in volume. So the work done will be 0. So isochoric, the answer will be 0. Then we come to isothermal. Okay, then we come to isothermal. Now what is isothermal? Isothermal means that temperature is constant. Now this isothermal, actually it has got a better discussion in second law of thermodynamics. There is a very good quality discussion on isothermal. But for the time being, just remember that there is another way of interpreting isothermal. If they say that the process takes place very slowly. Okay, so if they say that the process takes place very slowly, okay, so isothermal means temperature is constant, but if they say that the process takes place very slowly, then also we can say that it is isothermal. So either they will directly say it's isothermal, meaning temperature constant, otherwise they will say the process takes place very slowly. If they say process takes place very slowly, then also we can take it to mean that it is isothermal. So W is integral V1 to V2 P dV. So integral V1 to V2 P dV. So instead of P you write nRT by V. So integral nRT by V dV from V1 to V2. Now remember that it is isothermal. So that means in this formula nRT dV by V, T will be constant. So this is coming. So you know that integral dV by V is ln V. Okay, integral dV by V is ln V. So this will be nRT into ln V, but the upper limit is V2, lower limit is V1. So nRT ln V2 by V1. So integral nRT dV by V, V1 to V2 is nRT into ln V2 by V1. And you can also do one thing. You can write 2.303 nRT log V2 by V1. So nRT ln V2 by V1, this is ln means the base will be E. So you can write it as 2.303 nRT log V2 by V1, base is 10. So ln means base is E, and for log, of course, common logarithm, base is 10. So isothermal work done, the formula is this and this, both are the same, but the log base 10 is more comfortable for calculation purpose. So we use 2.303 nRT log V2 by V1 because that is more comfortable for calculation. So isobaric, isochoric, isothermal, and isothermal, it can also be said in another way that the process takes place very slowly. Then we come to adiabatic. Adiabatic means there is no heat transaction. So adiabatic means there is no heat transaction. So that means delta Q will be 0. So delta U will be equal to minus delta W. By the way, when it is isobaric, so delta Q will be delta U plus P delta V. When it is isochoric, then delta Q will be delta U. When it is isothermal, then delta Q will be equal to delta W. Okay, now remember this, all of you. This is important. Okay, if you are talking about an ideal gas, then the delta U, that is the total internal energy of the ideal gas, it only depends on the Kelvin temperature. It doesn't depend on anything else. So if you are talking about if you are talking about isothermal, then the delta U part will be gone. So delta Q will be delta W. So once again, isobaric, delta Q is delta U plus P delta V. Then, okay, isochoric means there is no work done, so delta Q is delta U. And isothermal means that the internal energy will be constant, that means delta U will be 0, because if it is an ideal gas, then internal energy depends on only one thing, that is the temperature. And since it is isothermal, the internal energy will not change. So delta Q will be delta W. Then we come to adiabatic. Adiabatic means there is no heat transaction. So delta Q will be 0, so delta U will be minus delta W. Now, the thing is, adiabatic we can also say in another way. Okay, adiabatic we can say in another way, like isothermal is process takes place very slowly, so adiabatic we can say it takes place very quickly. So isothermal is very slowly, adiabatic is very quickly. Okay, so if the process is adiabatic, then delta Q is 0, delta U is minus delta W, and adiabatic actually adiabatic process, actually there are a few formulas which have to be remembered. One is in any adiabatic process, pressure into volume to the power gamma is constant. I'll just tell you what is gamma. In any adiabatic process, pressure into volume to the power gamma is constant, number one. Number two, temperature into volume to the power gamma minus 1 is constant. So remember, if it is a adiabatic process, P into V to the power gamma is constant and T into V to the power gamma minus 1 is constant, right? And the third one is the work done. The third one is the work done So delta W is P1 V1 minus P2 V2 by gamma minus 1. So work done is P1 V1 minus P2 V2 by gamma minus 1. So this is the formula for work done. So adiabatic PV to the power gamma constant, TV to the power gamma minus 1 constant, and work done is P1 V1 minus P2 V2 by gamma minus 1. So these are the formulas for adiabatic. But what is gamma? What is gamma? That we didn't discuss. Now what happens is that in order to understand what is gamma, we need to do one topic called specific heats. So in adiabatic, PV to the power gamma constant, TV to the power gamma minus 1 constant, and delta W is P1 V1 minus P2 V2 by gamma minus 1. So in order to apply adiabatic, we must first understand what is gamma. So to understand what is gamma, first we have to do one topic called specific heats. Okay, so specific heats. First is CV. Okay, CV is heat supplied by N into delta T at constant volume. And what is CP is delta Q by N into delta T at constant pressure. So what is this CV? It is molar specific heat at constant volume. So CV is delta Q by N delta T. So it is molar specific heat at constant volume, that is CV. Then what is CP? Then what is CP? CP is molar specific heat at constant pressure. So the molar specific heat at constant volume, the symbol is CV, is heat supplied by N into delta T, and molar specific heat at constant pressure is CP, that is heat supplied by N into delta T. So this is CV and this is CP. So these are the molar specific heat at constant volume and constant pressure. Okay, now so delta Q is delta U plus delta W. So if the process is taking place at constant pressure, then delta Q will be N into Cp into delta T, right? So it is constant pressure, so delta Q will be N into Cp into delta T, that is delta U plus, and delta W will be P into delta V. It is constant pressure. So this will be the equation. So at constant pressure, N into Cp into delta T is delta U plus P delta V, and at constant volume, NCV delta T is delta U plus 0, because constant volume there is no work done. So NCV delta T is delta U plus 0. So at constant pressure, NCP delta T is delta U plus P delta V. At constant volume, NCV delta T is delta U. So if you combine these two equations, like this one and this one, then after combining these two equations, you will get NCP delta T is NCV delta T plus P delta V. So if you combine this and this, NCP delta T is NCV delta T plus P delta V. So now you divide both sides by N delta T. So Cp is Cv plus P delta V by N delta T, right? You divide throughout by N delta T. So Cp is Cv plus P delta V by N delta T. Meanwhile, you are aware that PV equal to nRT. Okay, meanwhile you are aware that PV is equal to nRT. So P delta V will be nR into delta T, right? PV is nRT, so P delta V will be nR delta T. So P delta V is nR delta T. So you have to remember that in this equation the pressure is constant. So PV equal to nRT. In this equation pressure is constant. So PV is nRT. If you differentiate both sides, or if you take increments on both sides, so P delta V will be nR delta T. That means P delta V by N delta T will be R. So Cp will come Cv plus R. Okay. So NCP delta T is NCV delta T plus P delta V. So Cp will be Cv plus P delta V by N delta T. Now PV is nRT. So if you take differential on both sides, so P delta V is nR delta T. So P delta V by N delta T is R. So P delta V by N delta T, you write R. So Cp will be Cv plus R. Okay. So Cp will be Cv plus R. Now, what is gamma? What is the ratio of Cp and Cv called? So, what is the ratio of Cp and Cv called? So, the ratio of Cp and Cv is called gamma. Okay, so the ratio of Cp and Cv is called gamma. So a few minutes back we were doing adiabatic, and I was telling you that later on I will tell you what is the meaning of gamma. So Pv to the power gamma constant, Tv to the power gamma minus 1 constant, work done is P1 V1 minus P2 V2 by gamma minus 1. So the ratio will be Cp by ratio of Cp by Cv is called gamma. So the formula is Cp equal to Cv plus R. So instead of Cp you write gamma into Cv. So gamma into Cv is Cv plus R. So Cv will be equal to R by gamma minus 1, and so Cv will be equal to R by gamma minus 1, and Cp will be R gamma by gamma minus 1. Okay. So CV, by this equation, CV will be R by gamma minus 1, and this CV, if you put it here, Cp will be R gamma by gamma minus 1. So now you know exactly what is gamma. So gamma is the ratio of Cp and Cv, the ratio of specific heat, that is called gamma, right? So, so basically we have discussed two types of specific heat. One is molar specific heat at constant volume and one is molar specific heat at constant pressure, and the ratio of both of them is called gamma, and Cp and Cv in terms of gamma is this, right? Now apart from Cp and Cv, what other specific heat you need to know? One is specific heat of solids and one is specific heat of water. So now let us discuss those two, specific heat of solids and specific heat of water. Okay, so these two topics are left, specific heat of solids and specific heat of water. These two topics are left. Okay, now the thing is that in order to write down the specific heat of solids and the specific heat of water, you need to find out the degrees of freedom. Okay, you need to find out the degrees of freedom. Okay, So degrees of freedom, what is it? So degrees of freedom is the number of independent terms in the expression of energy of a molecule. So suppose you are writing down an expression for the energy of a molecule, then the number of independent terms in that expression is called degrees of freedom. So first is monoatomic gas. So first is monoatomic gas. So monoatomic gas, along x-axis the kinetic energy will be half mvx square, along y-axis it will be half mvy square, and along z-axis it will be half mvz square. So suppose if you are discussing a monoatomic gas, along x-axis it will be half mvx square, along y-axis half mvy square, and along z-axis it will be half mvz square. So in the energy of a monoatomic gas molecule, in the energy expression there will be three independent terms, half mvx square, half mvy square, half mvz square. So that means that the degrees of freedom will be 3. So a monoatomic gas molecule will have 3 degrees of freedom, this one and this one. So monoatomic gas molecule degrees of freedom will be 3. Then we come to diatomic gas. Now, regarding diatomic gas, there is half mvx square, half mvy square, half mvz square, plus half ix omega x square plus half iy omega y square. So, how is this coming? Actually, in a diatomic gas, we can assume that the two atoms which are there in the molecule, they are connected by a massless rod. Suppose the two atoms, it's a diatomic gas molecule, so there will be two atoms. So suppose the two atoms are very tiny rigid spheres and they are connected by a massless rod, and this massless rod is suppose this massless rod is placed along the z-axis. So this sphere and this massless rod, it can rotate about the x-axis. This whole system can rotate about the x-axis. So half ix omega x square. It can rotate about the y-axis. So half iy omega y square. and kinetic energy can be along x, so half mvx square, along y half mvy square, and along z half mvz square. And along z there won't be any rotational kinetic energy because it is situated on the z axis. So there cannot be any rotational kinetic energy about the z axis. So you can have 3 degrees of translational freedom and 2 degrees of rotational freedom, like 1, 2, 3, and these two are for rotational. So the degrees of freedom will be 5. The degrees of freedom will be 5. Now one thing you have to remember, for diatomic gases, the degrees of freedom is always 5 except when the temperature is very high. Okay? Except when the temperature is very high. If the temperature is very high, then apart from 3 degrees of translational and 2 degrees of rotational, you will also have to consider vibrational and potential. So at very high temperature, half mvx square plus half mvy square plus half mvz square plus half ix omega x square plus half iy omega y square plus potential energy plus vibrational energy. So half mvx square plus half mvy square plus half mvz square plus half ix omega x square plus half iy omega y square plus potential energy plus vibrational energy. So the degrees of freedom will be equal to 7. So diatomic gas at normal temperature, degrees of freedom will be 5, and at very high temperature, the degrees of freedom will be 7. So the next thing is polyatomic gas. Okay, now before we discuss polyatomic gas, we will have to discuss So before we discuss polyatomic gas, we need to discuss the law of equipartition of energy. So what is this law of equipartition of energy? We need to discuss that. So, average energy of a molecule associated with each degree of freedom. So, average energy of a molecule associated with each degree of freedom is equal to half kT So K is called Boltzmann constant. So K is called Boltzmann constant. And T is called the Kelvin temperature. So what is law of equipartition of energy? Average energy of a molecule associated with each degree of freedom is half kT. K is the Boltzmann constant and T is the Kelvin temperature. Okay. Okay, now when we were doing monoatomic and diatomic, while doing monoatomic and diatomic, we had done one thing, that we had taken a translational kinetic energy, rotational kinetic energy, and in diatomic we took vibrational and potential in diatomic. Now what happens is that when you say translational kinetic energy, rotational kinetic energy, or even potential energy, then half kT is applicable. Like suppose for example half mv x square, so 1 degree of freedom, half mv y square, 1 degree of freedom, like that. Then half ix omega x square, 1 degree of freedom, like that. Then potential energy is 1 degree of freedom. So all of them will be half kT. But the vibrational energy, actually it has been thought that vibrational energy is nothing but a combination of kinetic and potential. Okay, it was thought that vibrational is nothing but a combination of kinetic and potential. So for vibrational energy, the calculation will be half kT plus half kT, that is equal to kT, right? So it is actually, the formula is half kT for each degree of freedom, but if it is vibrational energy, then it will be half kT plus half kT, that is equal to kT, right? So that means what? That internal energy calculations Now you know that, so let us do the internal energy calculations for different type of molecules like monoatomic, diatomic. Now you know that delta U formula is NCV delta T. Now you are telling it is monoatomic. So monoatomic has 3 degrees of freedom, and for each degree of freedom it is half kT. So for 3 degrees of freedom it will be 3 times half kT, so 3 by 2 kT into the number of molecules. Number of molecules will be number of moles into Avogadro. So 3 by 2 kT number of moles into Avogadro is equal to number of moles into Cv into delta T. So now actually, since everything is delta, so this is delta U delta T. So here we can write 3 by 2 K delta T. Number of moles into Avogadro is N into Cv into delta T. So now let us cancel delta T. So Cv will be 3 by 2 into N, sorry, N is also getting cut. So 3 by 2 into K into Avogadro. So this is 3R by 2. So 3 by 2 into K into Na is Cv. So K into Avogadro is R. So Cv will be 3R by 2. So Cp will be Cv plus R, that is 5R by 2. And gamma will be Cp by Cv, that is 5 by 3. So Cv will be 3 by 2 Kna, that is 3R by 2. Cv will be Cv plus R, 5R by 2. And gamma will be Cp by Cv, that is equal to 5 by 3. So gamma will be 5 by 3. Next, let us go to diatomic. So NCV delta T. So delta U is 5 by 2 K delta T into N into Avogadro is N into Cv into delta T. So cancel the N, cancel the delta T. So Cv will be 5R by 2. And Cp will be Cv plus R, that is 7R by 2. So gamma will be Cp by Cv, that is 7 by 5. So Cv will be 5R by 2, Cp will be 7R by 2, and gamma will be Cp by Cv, that is 7 by 5. Now suppose if you are doing suppose if diatomic gas is at high temperature, then over here 5 by 2, like 5 degrees of freedom, and then what you have to do is for vibrational you have to consider 2 degrees of freedom. So if it is high temperature, then 5 degrees of freedom for like kinetic energy, and one for like vibrational has two, like vibrational has potential and kinetic both. So this will become 7 times so 7 by 2 k delta T into n into Avogadro is n CV delta T. So this will get cancelled, n will get cancelled. So CV will be 7R by 2. Okay. So CV will be 7R by 2. And Cp will be Cv plus R, that is 9R by 2. And gamma will be Cp by Cv, that is 9 by 7. So if it is diatomic gas, Cv is 5R by 2, Cp is 7R by 2, gamma is 7 by 5. And if it is diatomic at high temperature, Cv will be 7R by 2, Cp will be 9R by 2, and gamma will be 9 by 7. Then we come to polyatomic gas molecule. Okay, now if it is a polyatomic gas molecule, then for translational kinetic energy we will take 3 degrees of freedom. Okay, if it is a polyatomic gas molecule, for translational kinetic energy we will take 3 degrees of freedom. For rotational kinetic energy we will take 3 degrees of freedom. And for vibrational we will take a figure F. So F will depend on the atomicity of the molecule. So F is something we will keep it as a variable. So translational 3, rotational 3, and vibrational we will keep it as F. So delta U is NCV dt. So 3 2s are 6. 3 plus 3 6. And for vibrational 2 into F. So 6 plus 2F into half K into delta T into number of moles into Avogadro is NCV into delta T. So Cv is coming 3 plus F into R, and Cp will be Cv plus R, so 4 plus F into R. So Cv will be 3 plus F into R and Cp will be 4 plus F into R. So this is for the polyatomic gas molecule. So that means for polyatomic gas molecule, the value of gamma will be this. So Cv is 3 plus F into R, Cp is 4 plus F into R. So gamma is 4 plus F by 3 plus F. This is for polyatomic gas. Okay. So after polyatomic gas, next is specific heat of solids. So delta U is equal to N into Cv into delta T. So instead of delta U, you write 3K into delta T. This is per molecule. So into number of moles into Avogadro. Now what is the logic? Actually in a solid we don't have anything called kinetic energy, so it's only vibrational. But vibrational energy we will take it in 3 dimensions. So for a solid we will, vibrational energy, it will be potential plus kinetic, so 2 into half kT into 3 dimensions, this into 3. So that is 3 kT. And delta U is NCV delta T. So instead of delta U we will write 3K delta T into number of molecules is N into Avogadro is NCV delta T. So now if you cancel delta T on both sides, so Cv is equal to 3R. So and why are we doing Cv only? Why we will not do Cp? Because in a solid change in volume, if at all any change in volume, it is negligible. So there is no need to do Cp. So in a solid, the only thing you have to remember, there is no kinetic energy, it's only vibrational, but in 3 dimensions. So 2 into half kT and then into 3 because of 3 dimensions. So the answer is 3 kT. Delta U is NCV delta T. So 3K delta T into number of moles into Avogadro is NCV delta T. You cancel delta T, you cancel N. So Cv will be 3 into K into Avogadro. So Cv will be 3 into R. Okay, now we come to specific heat of water. Now when you are doing specific heat of water, so we will treat water like a solid. So when you are treating water you treat it like a solid. So delta U will be 3 into 3K delta T into number of moles into Avogadro. Acha. Now why do we multiply 3K delta T with 3? Like here it is 3K delta T, but here it is 3 into 3K delta T. Why? The reason is that water water molecule has 3 atoms. So there is 2 hydrogen and 1 oxygen. So because water molecule has 3 atoms, so it will be 3 times of this. So 3 times of 3K delta T into number of moles into Avogadro is number of moles into Cv into delta T. So Cv will be equal to 9R. So if you treat water like a solid, then you only have to consider vibrational energy. But the important thing to remember is that the water molecule has 3 atoms, and therefore when we say 3 into K into delta T, that is for 1 atom. So for 3 atoms it will be 3 times of that. So we will get Cv equal to 9R, right? Okay, so what we have done today in this meeting is that we have completely discussed first law of thermodynamics. Like we have discussed what is the first law, we have discussed what are the different formulas of work done, isochoric, isobaric, isothermal, adiabatic, we have discussed all that. Then we have discussed what are the different types of specific heat. So specific heat at constant pressure, specific heat at constant volume, we have discussed that. Then relation between them, Cp equal to Cv plus R. Then we have discussed the law of equipartition of energy, which says that the energy associated with each independent term in the energy expression, okay, that is called degree of freedom. So monoatomic has 3 degrees of freedom, diatomic at low temperature has 5, high temperature has 7, and polyatomic is low temperature is 3 plus F and high temperature it is 4 plus F. So we have discussed all that, and then finally we discussed for solids, and then we discussed for water. So these are all the different concepts, and then of course we discussed how to find Cv for monoatomic, diatomic, polyatomic, how to find Cv for solids, how to find Cv for water, and correspondingly how to find gamma for monoatomic, diatomic, polyatomic, all that we have discussed, right? So what we have managed to do today is that we have completed first law and the remaining portion of kinetic theory beyond whatever we had done the last day. So we have completed the whole thing, right? So that means first law of thermodynamics and kinetic theory, both the topics are over. So I think we were doing Doppler effects, so we may go back to oscillation and waves, or we may do thermal properties of matter, either one. So, but these two chapters are over, first law of thermodynamics and kinetic theory, right? So that brings us to an end of this particular session. Okay, thanks a lot, and I am hereby concluding this session. Thank you. Bye all of you.